Hello, my name is Nicholas Bramhall, and this is my lab report for Lab 2. Excuse me for talking fast to get through this so I don't waste you guys' time. So, here's the introduction. Now, the purpose of this lab is to discover the effect drag has on an object in freefall. The result was that we discovered that drag had a noticeable reduction on an object's velocity in freefall, especially in the x, which narrows its trajectory. And then the system was the ball in motion, and surroundings was everything else. Here are the principles and equations. The main principle used is Newton's second law, the momentum principle, which is simplified in F net equals ma. We need the ma in order to find the acceleration that's used to update the velocity before updating the position. How we calculate the net force is by adding together the F drag and the F gravity, the force of gravity, which is shown in these two equations. Notice how drag is based solely on velocity and a constant. Now, the methodology is you take a ball and you throw it. You record that throw in order to analyze the path and tracker. Using that data from tracker, we can derive the initial conditions used in the code model to simulate the path with just gravity, and then again with drag included. Finally, we compare the three to understand how drag affects the gravity model and correlates with the real-life experiment. Here's the code model. You can see in the upper half, these are the initial conditions. And then in the lower half, we have the iterative loop. Now, this loop is updated each 0.1 second. So we update the drag every 0.1 seconds, and then we update the velocity, and then we update the position using the data from above. Now, here are the data and results. This is the tracker, and that's the data values used in order to calculate the initial conditions. And then here we have the output of the drag model of the code. And then finally, we slotted all three of them onto this graph right here. The tracker module, the tracker code data, is the upper one, the one above all the other ones. And then, interesting enough, we have gravity going below it. And then you can see that the drag one is below it. However, you can see that despite running all for the same time, it didn't go as far, showing that the drag worked in the x, and then it didn't go as low, showing drag worked in the y. Now then, the discussion. What if instead of throwing the ball at like a 45-degree angle, it's thrown straight up with the same initial speed, meaning it had the same magnitude? Well, if you look at the equation where it's g equals velocity times time plus 1/2 acceleration times time squared, you would notice that in that case, with the initial velocity being higher, it has more initial velocity it has to overcome before it can stop becoming negative. And meaning it goes up for longer and thus has more area to come down, and thus it's just overall longer. And conceptually, it makes sense too if you throw a ball straight up rather than forward. It's going to take longer to hit the ground. Now, what does this experiment mean? Or what does it mean for the model predicting terminal velocity? And the answer is no. The model did not predict terminal velocity in any of them, because in order to accomplish that, we would have to drop the ball or throw the ball up from a high enough point so that it accelerates to where the magnitude of the velocity would be so great that the drag force equals the gravity. That would be an immense velocity, and it would also have to be thrown directly upwards so that the x velocity reaches 0 before that point. You could throw it straight, but there is a possibility of it reaching terminal, like where the drag force equals the gravity, but then you still have that drag force coming from the x. Because once the drag force passes the gravity and the y, you can't go back to that. Now, possible human error. There's some possible human error in recording the video. For example, if the angle of the video was a little bit off, wasn't completely flat, the calibration meter stick could be a little bit off. However, it should not be substantial. Now, in tracking the video, there could be a lack of position in placing the point of the ball. However, for most of the tracker, it was almost dead center in the middle of the ball. And then finally, inaccurate initial conditions due to inaccurate calculations. However, the calculations have been completed multiple times and done by multiple people, and they've all turned out the same, and thus we can have confidence that the initial conditions are accurate. Now, conclusions. The conclusion was that drag had a narrowing effect on the trajectory, shown by the fact that comparing the gravity and the drag one, the drag was a little bit below, it was kind of narrow, and it was a little bit up. But also, we can also notice that even simple code models such as the gravity can be off if given alongside data, shown by how the gravity was below the tracker data, even though conceptually it should be above. Thank you for your time. I hope you guys have a good day. Thank you.